Okay, good morning, everybody. So today, as I announced yesterday on the website, we're going to have like a very practical lecture trying to introduce PyTorch, which is this library for training neural networks. So if you have never worked with PyTorch or even never worked with the training of a neural network, I think this is pretty useful. I'm actually adding this lecture, which was not there last year, because many students asked me last year to do it. So of course, they asked me too late. They asked me at the exam, but I took into account their feedback. So please give feedback, because I do change stuff according to what you tell me. Of course, it's too late for you, but students for the next year will benefit from it. So in the final project, I still haven't decided what the final project should be this year, but very, very likely you're going to have to work with neural networks, or at least you might have the chance to do it if you want to. And I recommend you to do it. It's a useful technology to know how to use. And so it's very useful to do this, because at least when you face the project, you already know a bit how to work with the neural network, and you don't have to learn everything on your own. You already have a good starting point. So we already discussed a bit what neural networks are last Friday in class, but that was very theoretical and abstract. Today it's going to be like the complementary of that. We're going to be instead very applied and practical. So this notebook that I'm using is inside the RL folder, and it's called Intro Neural Network Interact. So in case you want also to open it and play with it while I do play with it, I think it makes the lesson a bit more interactive for you, and probably you're gonna learn more if you do that. This one, I committed it yesterday, so you need to update the org repository, as you already did a few times, so you should know how to do it. It's either a git pull command, or you can just reclone the repository from scratch in case git pull doesn't work and you don't know how to make it work. Okay, let's start. Can make this a bit bigger. Well, first of all, we are just importing all the libraries that we need, where there is matplotlib, time just to measure computation time, copy, we'll see why we need this. And then the main new entry here are all these different modules of the PyTorch library. So the main namespace for the PyTorch module is just torch, but then it is divided into other namespaces. So we have NN, which stands for neural networks, Optim, which contains the optimization algorithms, and functional is just a way to get the activation functions. One of the key features of PyTorch, and actually of probably all libraries for doing neural networks, is that you can either run stuff on the CPU or on the GPU. So in case your computer has a GPU, PyTorch may be able to use it for training the neural network. And of course, if you use the GPU, everything is going to be faster. It's not as simple as that to use it, because you need to be careful. If you have data on the CPU and you want to do the training of the network on the GPU, then you need to transfer data from the CPU to the GPU. And maybe if your network is not very big, actually, the time you take for transferring the data from CPU to GPU may actually be bigger than the time you save by training the network on the GPU. So it's not always convenient to go on GPU. It depends on your specific application. So I suggest you to do test Just don't go blindly on the GPU because the GPU is faster, period. It depends, okay? And if you have a Mac, I don't think you will be able to use the GPU. At least I'm not. I was never able to use my GPU with these neural network frameworks. If you have instead Linux, probably, or maybe even if you're working with the Windows subserver for Linux, WSL, probably you can use the GPU in those cases. So to know whether PyTorch is able to detect the GPU on your machine, you just need to execute this first piece of code, and it's gonna print going to use, and then either CPU or GPU. Well, it's gonna be either CPU or CUDA. CUDA is the library designed by NVIDIA to exploit NVIDIA GPUs for doing like linear algebra computation. So there is this command here, torch.cuda.isAvailable, which returns true if PyTorch has detected an NVIDIA GPU on your machine, or false otherwise. So in my case, it returns false. And so the device that I'm going to use for the neural network training is the CPU. So if I execute this, it tells me going to use CPU. Anybody who is running this has the CUDA GPU detected? Okay, doesn't matter. I mean, for today especially, we're going to work with a super small scale neural network, so it's probably not even worth it to go on GPU with this one. First of all, we're going to define the structure of the neural network. And we have seen last time that neural networks are structured in layers, and then each layer is made of a list of neurons. So in this specific case, we're going to work with a neural network which has one input layer, one output layer, and that's always the case. You always have one input and one output layer. And then what you need to decide is how many hidden layers you need to have. That was supposed to be an S. And the higher the number of hidden layers, the bigger the network is going to be. It's actually going to be called a deeper network. So deep neural networks are networks which have many hidden layers. In this case, it's not very deep. It's rather shallow because we only have two hidden layers. And then you can decide how many neurons each layer has. And of course, the higher the number of neurons, the higher the number of parameters of your network, and the more like powerful in terms of capability of approximation the network is going to be. Of course, it's a trade-off. As you add layers and neurons, your network is more powerful. It can approximate like more functions to a higher level of accuracy, but you have more parameters, which means that it takes longer for training, and it takes more data for training as well. So you always need to be careful when you tune these hyperparameters, when you choose the number of layers, the number of neurons. I think it's quite useful to think of how many data points you're going to use for training the network. And typically, it's a good rule of thumb to not have more parameters of the network than data points. Actually, I would go for having like many more data points than parameters, maybe 10 times more at least. And another thing that you have to decide when you create the network is the activation functions. You can use different activation functions for the different layers. That's okay. We are not going to do that. To keep things simple, we're going to use the same activation functions for all the neurons for all the layers. And that activation function is going to be the ELU, which has a name that reminds a lot of ReLU, and that's not by accident, because that's supposed to be an approximation of the ReLU. So the ReLU is way more standard, but the reason why I want to push you towards the ELU is that the ELU is smooth. And so it's differentiable everywhere. And so in case you need to use this network inside an optimizer later on, like maybe you want to use this network to approximate a value function that you use as a terminal cost in an MPC, for instance. That's something that we did in the past. ELU is much better than ReLU because it's smooth. And so the optimizer is gonna behave better if you have a network with ELU activation functions that are smooth rather than with ReLU. The training performance is actually typically better with ReLU. So if your objective is just learning, like training a neural network to learn the data set as good as possible, probably ReLU is going to do a better job. But if then you want to use this network inside an optimization problem, ELU is better. Okay, so in this case, we're going to use ELU. Yeah.
Better to have more layers and less neurons, or the opposite?
So there is no strict rule. In theory, so what the theory of neural networks says is that if you have just one hidden layer with a sufficiently high number of neurons, that's good enough for learning any function. Okay, so that would suggest just use one hidden layer and augment, increase the number of neurons until you reach a performance that you want. That's the theory. The practice says the opposite. It's actually better to increase the size of the network in terms of layers than to make each layer very, very wide. So deep networks, they seem to work better in practice than wide networks. So of course you need also some width. You cannot make hidden layers of one neuron and expect things to work well, no. But probably after a certain point, it's not so convenient to increase the number of neurons. It's better to increase the number of layers. But again, it's a trial and error, basically. So this is a code for defining the structure of the neural network in PyTorch. We need to create a class. You can choose whatever name you want. I've chosen this simple network name. And this class needs to inherit from nn.module, which is the parent class for all neural networks. And then you need to define at least these two methods, the constructor and the forward method. So in the constructor, what we do is that we create all the linear part of the network. So first of all, we take as inputs the number of inputs, the number of outputs, and the number of neurons in the hidden layers. By default, I set that to 16, but you can specify a different value if you want when you create it. With this line, we call the constructor of the parent class, which is nn.module. We always need to do that. And then we create three linear layers. And when you create a linear layer, you need to specify the number of inputs and the number of outputs of each layer. So the first linear layer is the one that maps the inputs to the hidden layer, to the first hidden layer. So the input size is n inputs, and the output size is n hidden. Then the second linear layer maps from hidden to hidden layer. So the input and the output sizes are the same, which is n hidden. And the last linear layer maps from the second hidden layer to the output layer. So input size is n hidden and output size is n outputs. this covers only the linear part of the network. You remember that at each layer, the inputs are all combined in a linear fashion. And then whatever is the result of that linear combination of the inputs goes through the activation function. The activation function, we call it here inside the forward method. So the forward method takes as input the inputs of the network, and it returns the output of the network. So it's the one that basically evaluates the network for a given input, and it gives you the outputs. So what we do with the inputs is that we make it go through the first linear layer, so layer 1. So first of all, we take a linear combination of the inputs. Whatever we get as an output goes through the ALU activation function. So the ALU activation function works element-wise. So if you pass to it a vector, it's going to apply the ALU function to each element of that vector, and it's going to give you as outputs a vector with the same size as the input vector. So it's an element-wise application of the function. Whatever we get as output, we always call it X, and we make it go through layer 2, which is again another linear layer. The output of layer 2 is again processed by the ALU function. And what we get as an output of the ALU function goes through layer 3, which is yet another linear layer. And layer 3 gives me an output which has the size and outputs, and that is what I return. So we have linear layer, ALU, linear layer, ALU, linear layer. That's how the network works. Of course, here it's pretty easy to modify the structure of the network. If you want to add more layers, if you want to use different activation functions, you can just look online at the documentation of PyTorch. There are plenty activation functions that you can use. Hyperbolic tangents is another very common one, which is useful when you have like maybe bounded outputs. The hyperbolic tangents is useful because it's bounded. And so you can be sure that if your last layer is a tanh layer, the outputs are going to be between -1 and 1. And then, of course, you can scale this by whatever constant you want to make it be between different values. And when you execute this cell, it does nothing because you're just defining a new class, but you're not creating anything actually. Okay, so now that we have defined the structure of the network, we need to create it. We need to instantiate an object of that class. And at the same time, we will also create the optimizer. That's the optimization algorithm that we will use for training the network. Last time in class, I've talked about stochastic gradient descent, but I've also told you that in practice, people don't use like vanilla stochastic gradient descent, but there are some extensions to stochastic gradient descent which are outperforming it. One of them is called Adam, and that's the one we're going to use. And we will also define the loss function for training. The loss function, if you remember, is the objective function of the optimization problems that you solve when you're training a neural network. It's basically a function that measures the error that the network is making in approximating the data points. A very classic loss function is the mean squared error. So you measure the difference between the expected output of the network and the current output of the network for a given input. You take the difference and you take the squared to norm. And this is the code for doing that. So it's a function which I called create network. It takes as input the learning rate. And inside the function, what we do is that we instantiate the network. So we call simple network specifying the number of inputs and the number of outputs. In this case, we're going to work with a network which has a one-dimensional input and a one-dimensional output. The reason is that so we can plot everything very easily. But the code is going to work even if you scale this up to multiple dimensions. And then this to device is basically useful when you're working on GPU. This is moving all the network data on the GPU so that you can do the training there later on. Here we instantiate the optimizer, which is, as I told you, Adam. When you create the optimizer, you need to give it the parameters of the network, because those are going to be the decision variables for the optimization problem. And you need to specify the learning rate. Again, for the learning rate, there is no strict rule for what value it should take. But in practice, typically people tend to use values between 10 to the minus 3 and 10 to the minus 4. So that's the range you should be looking at. And finally, we define the loss function, which is simply the mean squared error loss. So there is already a class in PyTorch that defines this loss function, which is a very common one. In general, you don't need to work with a pre-specified loss function. You can also define it yourself. But if you're using a standard one like the mean squared error loss, it's more convenient to just use the class that's already predefined for you to use. But you can get creative and come up with another kind of loss function which is not predefined inside PyTorch. And this is the definition of the mean squared error loss. Hoping it comes back to life. Okay. So you can see it's simply the summation over your data set of phi evaluated at the input I minus the output I in norm squared, where phi would be the neural network function, in is the input, and out is the output. Okay, so now we have the neural network, the optimizer, and the loss function. Now we need the data. So for this simple example, what we're going to try to do is to learn a neural network that approximates this function here. This function is actually very simple. It's just a cubic polynomial. It's basically x to the power of 3, but it has a couple of parameters, x max and y max. So x max is for scaling the input, and y max is there for scaling the output. So we can make the input and the output take different scales. The reason why I've introduced these two parameters is that I want us to play a bit with the scaling of the inputs and the outputs of the network to see the effect that it has on the training performance, because that's quite important in practice. Okay, but just to begin with, you can think x max is 1, y max is 1, and so this is simply x to the power of 3, period. Super simple function. And here you can see I've written some code that defines the function f, which takes as input x and the two parameters x max, y max, and also a flag called add noise. because typically the data that you have when training a neural network is not perfect data. It has some noise. And so when the flag add noise is set to true, what we do is that we add some Gaussian noise to the function so that the network has a bit of a harder life learning this function. And then I'm simply using this code below here just to plot the function. You can see it here. Well, it's a cubic polynomial. It looks like that. It passes through 0. It goes positive for positive inputs, and it goes negative for negative inputs. Quite simple. It's a smooth function, so we shouldn't have too much trouble approximating this. Okay, so this is the function. Now we need to create the data set. And this is something that I think I didn't tell you last time, but typically when you're training a neural network and you have a data set, what you do is that you don't use all the data for training, but you split the data set in two parts. One part is the so-called training set, and that's the data that you're going to use for training the network. But then you leave out a certain number of data points, maybe like 20%. That's a quite common percentage. And that's going to be your test set. And that's super important because you want to use this test set, which is not used for training, to validate if the network is actually learning well the function and is not just overfitting over the training set. Because what could happen is that if you use all your data for training, the network learns very well to fit the data points, but in between the data points, the function is complete nonsense. That can happen, okay? So leaving out a few data points is very useful to check whether in between the training data points, the function is behaving as you would like it to. So if you're generalizing, that's the terminology that is used. If when you're outside the training distribution, the approximation of the function is still good. Because very often what happens is that the performance on the training set keeps getting better and better as you train more and more. But the performance on the test set gets better at the beginning, but then after a while, it stops improving and it starts worsening. And it's at that point that you want to stop training. When the performance on the test set starts getting worse. Okay, so that gives you a way for stopping training when you're at the best, basically. So this is a very useful thing to know. So what we're going to do now is that we're going to create a training set and a test set. And this is the code for doing it. So we simply sample in the input space a certain number of data points, which is specified by this parameter train size. And then for each of these inputs, we evaluate the function f. And since we haven't specified anything, we can check that by default, there is this flag add noise, which is equal to true. So this data that we generate is going to have noise on top. And we do that a second time for the test set. So we have two data sets, basically, with inputs and outputs for training and inputs and outputs for testing. This the first four lines creates the data set in NumPy. And you can see that we are using np.random.uniform for creating the inputs. So these are going to be NumPy arrays. And when we pass this data to the function f, we're going to get also NumPy arrays as outputs. However, when you train the network in PyTorch, you want to use torch vectors. Okay, so those are data structures defined by the library PyTorch, and those are the ones you should be using for training the network. So what we do is that we call this function from NumPy, defined inside the torch namespace, which takes as inputs a NumPy array, and it converts it to a torch array. Okay, so this data now is in torch format. It's exactly the same data. We haven't changed anything to it mathematically. We are just changing the data structure that contains the data. And this function then returns these four data structures, these four torch arrays. Oh, I forgot to execute the previous function. Okay. This is simply a function for plotting the data. So I'm simply plotting the original function without any noise together with the training set and the test set. Yeah.
Training set and test set as the same dimension.
No, we haven't defined yet the dimensions, but it's gonna be much bigger for the training set. It's typically like 80% training set, 20% test set.
But in this code,
It's gonna be 80-20. That's a pretty common ratio.
and where you find this?
It's gonna come later. It's gonna come probably here. Okay, you see training set 80, test set 20. These are not percentages, these are like absolute numbers. So in this case, it's really 80 data points and 20 data points. So you can see this is the function. In orange stars, we can see the training set. And in green triangles, we can see the test set. And you can see that there is noise because the points are not exactly on top of the real function, but they are a bit scattered all around it. So what the network is going to use for training is only the orange points. And from the orange points, ideally, we would like it to learn the real function, which is the blue line. Of course, without the noise, things would be a bit easier, but I think it's much more realistic if we have some noise in the data, because typically that's what you have in real life. Even when you're using actually a synthetic data generation, which is probably what you will need to do. Like, for instance, when you're learning a value function, the data that you use for feeding the network training is going to come out from an optimization problem. So you're going to solve an optimization problem, an optimal control problem, and the cost coming out from that is going to be the functions that you want to learn. So in that case, there is actually not really a noise on the data because the data is coming from a deterministic process. However, in practice, what we have seen is that even when you have synthetic data, sometimes the optimizer finds a local minimum that is different from the other local minimum that were found in that area. And that behaves a bit like if it was a noisy data point. And so even with synthetic data, actually, you kind of have something that looks a bit like a noise. Okay, so this is the function and the data sets. Now we can start training. So a few words about training. typically, when you talk about training, you to decide how long you want to train, you define it as a number of epochs for which you want to train. What is an epoch? So an epoch is basically the amount of training that you need for seeing all the data points in your training set once. So how many iteration of training an epoch is going to be depends on your data set size and on your batch size. Because since we're going to do something like stochastic gradient descent, we are not going to use the whole data set for each training step, but we're going to sample a mini batch. Remember, we have talked about mini batches last time. So if you have like these 80 samples for the training set, you're going to sample maybe 10 of them randomly, and you're going to compute the gradient of the loss function on these 10 samples, and you're going to take a step of stochastic gradient descent using this gradient. So that's one training iteration. And then if your mini batch has a size 10, you will do 8 of these iterations so that you can see all the data set which has size 80. So doing 8 iterations with a mini batch size 10 for a data set of size 80, that's one epoch. Okay. It's just a way to basically define a measurement unit for training length, which is kind of normalized with respect to the size of the data set and the size of your mini batch. So at each epoch, what we're going to do is that we're going to store the loss function on both the training set and the test set, because later on we want to look at this loss function and see if it goes down, because that's actually what we want. And also, we're going to keep track of the weights corresponding to the minimum value of the loss on the test set. And that's because, as I told you before, typically what can happen, in this case, it doesn't happen so much because it's a super simple problem, but in more complex cases, it happens a lot, that the performance is always improving on the training set, but on the test set, it improves at the beginning, and at a certain point, it gets worse. And so what you want to do is you want to keep the weights of the network when the performance on the test set was at its peak. Here the code is too long, so let me go back to this visualization. So this is the training function, which takes as inputs, well, a lot of stuff: the network, the optimizer, the loss function, the training dataset, the test dataset, the number of epochs, and the batch size. So what we do is that, first of all, we set the network in evaluation mode, because we want to evaluate the loss function before training, just to have a starting point. So here we evaluate the loss function given the training data set. And what's a bit tricky with PyTorch is that by default, when you evaluate the network and the loss function, what you get as an output is a torch vector. But actually, what we would like to have is a NumPy instead vector. Because for plotting, you want to use NumPy stuff, not torch stuff. So to go back from torch to NumPy, you need to use this .detach.numpy. Okay. So .detach is going to stop the keeping track of all the function evaluation, which is used inside PyTorch for having automatic differentiation. And .numpy converts to NumPy. So in this way, what you get here, this loss train, is actually going to be just a scalar. So that's going to be the value of the loss function evaluated on the training set before training. So it gives you your starting point, which is going to be typically very bad because you haven't trained yet. And then we do exactly the same here, but on the test set for the same reason. We want to know the starting point. And we store these values inside this list, losses training and losses test. These are the lists that we are going to append data to during training to keep track of how the loss is moving. Then we define how many iterations per epoch we want to do, and that's the size of the training data set divided by the batch size and then approximated to the closest integer. So if the batch size is 10, the training size is 80, this is going to be 8, as with the example we just made before. Then we want to keep track of the minimum value of the loss function on the test set. So we initialize it with the value that we have before training, because for sure it's not going to become worse than that. And also the minimum value of the weights for the neural network. So the value of the weight that corresponds to the minimum loss function. We also initialize it with the initial value of the network weights. And that's why we actually needed the copy module, because it is what you do for copying the value of the weights. So you take net.stateDict that returns the value of the weights of the neural network, which are stored as a dictionary. You can take a look at that later on if you want. And then we make a deep copy of this value. You cannot just say weights mean equal net.stateDict without the deep copy, because otherwise it's just a reference to those values. So when the network weights are going to be updated, also your reference is going to see the updated values. You know, in Python, when you do equal, you're not making a copy, you're just copying a reference to that data. And so when the data is modified, also that reference is going to see the modified data. If you've worked a bit with C, C++, you should know the difference between passing data by value or by copy. Sorry, by reference. So in Python, everything is by reference by default. If you want to copy the value, you need to explicitly ask for it. Like in this case, you do copy.decopy. This is really copying the values in memory from one place to another. And so when the original values are modified, the copied values, they remain untouched. That's actually the most common source of error when you're writing Python code. So be really careful with this stuff. You should keep that in mind, especially for the final project. I spent weeks debugging these kind of errors back in the days. Okay, then we start really the training loop. We just take a measurement of the time before training, because we want to measure how much time we're going to spend for training. Then we do a loop for the given number of epochs. At the beginning of each epoch, we set the network in training mode. And then we do another loop for a certain number of iterations, which is the number of iterations for each epoch. We randomly sample from the training set. So to do this random sampling, what we do is that we call this function called randint, which gives me integer numbers between 0 and the training size -1. So if my training dataset has size 80, this is gonna give me numbers that are between 0 and 79. How many? Well, in this case, it's going to be how many as the batch size. Okay, so it's going to be something like maybe 10 or 15. So once I have these indexes, which are these integer values, I can use them to select data from the data set. So what I do is that I take the inputs corresponding to the indexes I just sampled. I take the outputs corresponding to the same indexes. I evaluate the inputs with the network, and then I evaluate the loss function given the output of the network and the target outputs. And this gives me the loss function. I just add the loss function to this value, the total loss, to keep track of the training loss for this epoch. And then this is where the magic happens in PyTorch. I reset the gradient computation. I automatically evaluate the gradient of the loss function by using this loss.backward method. And then I do an update of the weights of the network using this optim.step method. Okay, so with these 3 lines, basically, you're doing all the math of the training. So this is where you're computing the gradient of the loss function and using this gradient to update the weights of the neural network. And this is so easy because PyTorch has autodiff implemented inside. So any function can be automatically differentiated without requiring you to go through the manual analytical differentiation of the function. So we don't need to specify what is the gradient of the loss function. You just specify what the loss function is, and then the derivatives of the loss function with respect to the weight of the neural network, that's automatically computed. Okay, so that makes it very, very easy to train the networks. And that's the same feature we actually had in Kazadi. So in Kazadi, when we were solving optimal control problems, we never had to specify derivatives by hand, right? We just specified the loss function, the dynamics of the system, all the constraints that we wanted, and then we just called solve, and everything was solved automatically. So behind that, there is an automatic differentiation tool, which is taking all these functions that we are defining and differentiating them with respect to the decision variables of the problem. That's why everything works so fast, because you have basically it's as if you had analytical derivatives, but without going through the pain of doing the math on your own. Okay, so we do that for a certain number of iterations. And at the end, we just divide the total loss by the number of iterations we have just performed. And we append that value to this list losses training. And that is basically it for training the network. We could stop there. But we don't, because we want to have data to analyze after training. So what we do is that we set the network again in evaluation mode, and we evaluate the loss function on the test set, and we append that value to this list losses test. This torch no grad is to disable the gradient computation, because otherwise this could interfere with the optimization problems that we have here. This evaluation of the loss function on a different data set. So we want to make sure that any evaluation that you do during training, you do it inside one of these blocks, torch no grad. So that's all the autodiff features are disabled when you do evaluation. And then the last 3 lines are to keep track of the best value of the loss function on the test set. And when you find the best value so far of the loss function on the test set, you copy the weights of the neural network because those are going to be probably the best weight you're going to find. Well, those are the best weights you have found so far. You don't know if it's going to get better or not in the future, so you store them aside. At the end of the loop, you just measure time again so that if you want, well, we can uncomment this line. We can print how much time we have spent for training. Then here, there is a simple function I've defined for low-pass filtering the data. I'm going to use this later on to filter the list of the value of the loss on training and test sets, because these values are going to be quite noisy. And having a filtered version helps understanding the trend, whether it was improving or worsening. So it's a simple low-pass filter. I don't know if you know this way of doing a low-pass filter. Is pretty useful and easy to implement. You're basically parameterizing the low-pass filter with a single value, alpha, which is between 0 and 1. And depending on the value of alpha, the filter is more or less aggressive at filtering. And what you do is that each output of the low-pass filter is just a convex combination between the current input, so data I, and the previous output, which is filtered data of I minus 1. And you do this convex combination, so one of them is weighted by alpha, and the other one is weighted by 1 minus alpha. So if you use a high value of alpha, then the real data, the current data is going to have a higher weight, which means you're going to be filtering less. Instead, if you go for smaller values of alpha, then you're going to be filtering a lot because you're going to rely more on the previous value of the filter data, which contains it's like a weighted average of all the previous data that you have filtered. So actually, this filter turns out to be a weighted average with an infinite window with exponentially decreasing weights. So data that is older has a weight that is smaller, of course, with respect to data that is more recent. And the way that these weights are decreasing is exponential. Okay, well, just 3 lines of code for filtering data. And this is just a function for plotting the results. We low pass filter the losses on the training set, the test set, as I told you before. So we're going to print both the real data and the filtered data, but nothing very interesting actually going on in this function. We can just move on. And this is where we put everything together. So this is the function train and plot. So we need to specify the learning rate, the scale for the inputs, the scale for the outputs, size of the training set, size of the test set, number of epochs, size of the batch, of the mini batch. And then we just call all the functions that we have defined above to create the data set, train the network, plot results. And here we just call it. And of course, it doesn't work. Why it doesn't work? Probably I missed to define some function, name error. So let me do that, just rerun everything. Okay. So let me make this a bit smaller so the plots should fit. Okay, so let me describe what we're seeing here. First plot on the left, we are seeing mainly 2 things. The loss on the training set, which is the green curve, this one, and the loss on the test set, which is the red curve. And you can see both the filtered version and the real data, which is more noisy. And you can see that the filtered version is much easier to look at and see the trend. So as expected, the loss is smaller on the training set than it is on the test set. So that's quite common. So since the training data, the network actually uses them for training, it's able to fit them much better than the test data, which is not used for training. But at least it's going down on both of them until at this point here. And then you can see there is a bit of stagnation or even actually worsening on at least on the test set. But even on the training set is actually saturating basically at this value. It's not able to go below that value. Typically, these kind of plots, you see them having the epochs on the x-axis, and here on the y-axis, you have the value of the loss in logarithmic scale. Because if you plot it in linear scale, it's not going to look good because you're not going to be able to see the difference of what's going on. It's going to saturate pretty soon and it's going to look flat, even if it's not actually flat. So it's much better to make them in log scale. Remember that for when you have to generate plots. On the right, instead, we see the real function that we are trying to approximate, which is the blue curve. You remember it's this x to the power of 3. And then you see two versions of the network function, red and orange. So the orange one is the network at the end of the training. And the red one is the network using the weights corresponding to the best value of the loss function on the test set. So that should be the best the network has gotten during training. And indeed, I mean, in this case, they're very similar because we can see actually that at the end of training, there is the value of the loss on the test set is not much worse than it was at its best moment, which was roughly here. And indeed, the two functions are pretty similar. And now what we can do is that we have these sliders above, which allow us to play with the parameters of training. Also here, total computation time for training 0.3 seconds. So it's pretty fast, which I mean, it should be because it's a super simple network. 1D input, 1D output. It should be super fast. So first parameter that we have here is the log of the learning rate. So now it's -2 by default, which means it's 10 to the -2. We can check what happens when we make this smaller or bigger. And every time you move it, so 9. Every time you move it, the curves are regenerated. I don't know why I have this layout problem, so I'm gonna just do it here. So for instance, in this case, I set it to -3 and performance just got terrible. You can see that there is not much improvement and the functions that we learn are basically straight lines, which are not really learning the real functions that I want to learn. You should consider that is a stochastic algorithm what we are running. Because every time we randomly sample the data sets and we randomly sample also the mini batches. And the initial value of the weight of the neural network, that's also random. So every time you run it, even with the same values for the inputs, you may have different results. So even with perfect input values, it's not always going to work great, even in these simple settings. It's painful, but that's life. So for instance, in this case, with 10 to the minus 3 as learning rate, it didn't work. But if we run it again, you can see now we have a different result. Still very poor, but a bit better than before. So for instance, in this case, maybe if we increase the number of epochs and maybe play a bit with the batch size. Okay. So this is a bit better. Well, it's much better, actually. I mean, at least this side of the function, we have learned it. We haven't learned this part here on the right, but it may very well be because we have very few data points on this final part of the input range. Because we can see that actually on the training set, the loss function is getting to a pretty small value, which is 10 to the minus 2, which means that the average error is 10 to the minus 2, which is pretty decent. It doesn't work as well on the test set, but I guess because we have some data here on the test set, but we don't on the training set. So here we are making some high error on the test set. I can try to make the learning rate even smaller. And in this case, there is basically no learning or very little learning. So here it doesn't matter how much I play with the other parameters. It's not learning, period. So clearly 10 to the minus 4 for the learning rate, in this case, it's too small. So we should work with bigger values, like 10 to the minus 2 was working very well. We can see as soon as we go to 10 to the minus 2, the fitting of the function is much better. So learning rate too small doesn't work well. What happens if we crank it up? Well, in cranking it up to 10 to the minus 1, we can see that now there is a big difference between the network at its best moment during training and the network that we got at the end. Any idea why? If you crank it up even higher, then it just doesn't work. Okay, now it kind of worked. We got lucky. With 1 as a learning rate, it's way too high. But if you use a learning rate 10 to the minus 1, okay, this one is great. Why does it do like that? Yeah, basically, when the learning rate is too large, what happens is that the training is very unstable. So it actually very efficient at the beginning. You can see that at the beginning, we start from very large loss, and we very quickly go to rather small values of the loss on both the training and the test set. You can see it here. And indeed, if we take the value of the network corresponding to the best performance, it's perfect. The red curve is perfect. But if we look instead at the network at the end of training, it's a flat line. So it's complete nonsense. It seems it has forgotten everything. And that's because with such a high learning rate, we are taking steps that are too big. And so instead of minimizing, so instead of improving the training, we are making it worse. And so after reaching this good performance here, it gets worse. Then it's able again to go down, but then it gets worse, it goes down, it gets worse. And you can see it's very unstable. And at the end, it's actually just going complete nonsense. So if you see this kind of curves for the loss function, then you know that the training is unstable, and you know you have to lower the learning rate. So in this case, 10 to the minus 2 seemed to be a very good value. It may depend on your specific problem. But typically that's the range, 10 to the minus 2, 10 to the minus 3, sometimes 10 to the minus 4, depends on the problem. You do a bit of trial and error by looking at the curves, and you're typically able to figure it out. Okay, then here we have the number of epochs for training. And of course, I mean, the more you train, the longer it takes, but typically the better the performance. Well, not necessarily, but actually we can see that for this example, we can get a pretty decent training even with just 200 epochs because it's a small data set, small network. So everything works quite efficiently. And then what's less obvious is the importance of scaling of inputs and outputs. Because so far, you can see it from these plots, we are working with inputs between -1 and 1, and also outputs between -1 and 1. You can see the range of the plots on the right, -1 and 1. So that's the ideal condition, okay? Let's see what happens if we change the scaling of the inputs. Like by moving this to 1, the inputs are now scaled between -10 and 10. Okay, so that's the log of x max. And here things are still fine. Between -10 and 10, we can see that the network is able to learn quite well. But what happens if we go to 100? It's exactly the same function. You can see the plot basically doesn't change. We are just changing the scaling of the inputs. And now we can see that the learning is not going well. And even if we increase the number of training epochs, it doesn't work. We can try to play with the learning rate, but it's not gonna help a lot. Okay, this time it's a bit better, but still quite weird. And you see, if I just rerun it again, it's not learning well. So here it's exactly the same algorithm, same function, same batch size, same learning rate, same everything. I've just changed the scaling of the inputs to be between -100 and 100, which is not even such a large scale. I mean, it's not a huge number. I'm not working with 10 to the power of 12, which is getting close to like the range of numbers that can be represented on a machine. We are still working with relatively small numbers, but neural networks are very sensitive to the scaling of the inputs. So that's why it's important when you use them Typically, your inputs are not going to be scaled between -1 and 1. They're going to have a different scaling. Your inputs may very well be the state of the robot, and maybe the velocities, they are between -10 and 10, for instance, or the angles are between -pi and pi. My suggestion is always scale the inputs between -1 and 1. That's gonna simplify a lot the training of the network. Of course, that means that the network is gonna work with these scaled inputs. So every time you want to evaluate the network, you're gonna need to take, for instance, the states of your robot, apply the scaling, and then evaluate the network on a scaled version of the state of the system. So it requires this extra step on your side to use the network. But it makes the training much more efficient and well functioning. So let's see what happens if we make the scaling of the inputs instead now smaller, so between -0.1 and +0.1. Well, it's kind of the same. So even going smaller, the network has troubles. Yeah.
But could you repeat why we have this behavior by scaling the input? We have the same amount of data.
Yeah, we have the same amount of data. It's the same optimization algorithm. I think it's mainly because we are not using second order optimization, but we are using like an extended first order method, which is stochastic gradient descent plus some tricks, which is Adam. And so these algorithms are much less robust to the scaling of data. So we didn't see this brittleness when we were doing trajectory optimization, right? We didn't need to scale the state, the control inputs to be between -1 and 1. And that was also an optimization algorithm like this one. But the difference is that when we were doing trajectory optimization, we were using basically second order optimization. So like Newton methods and variants of that. Here instead, we are doing something that is much closer to gradient descent. And we saw in gradient descent, for instance, that even if you're optimizing like a very simple quadratic function, but that has bad scaling, like 100x to the power of 2 plus y to the power of 2. So the curvature is not well defined, not well conditioned. Gradient descent fails miserably on those kind of functions. Here is kind of the same phenomenon that we are observing. And so since we cannot afford second order optimization, cannot afford to compute the Hessian and invert it because in general, the networks can have a very large number of weights. We need to do some work for making life easier for the optimization method.
So probably by changing the optimization function, we will reach better results.
It's not the optimization function, it's not the loss function, it's the optimization method. So the math that defines how you update the weights. That's the key part. Even the loss function could play a role, but I think it's mainly the optimization algorithm. So the optimization algorithm that we are using here, they are much more efficient than second order methods that we use for optimal control. But the price to pay is that they're also much less stable and robust. So too big or too small scaling of the inputs doesn't work. We can try now also the scaling of the outputs. So scaling of 10, it's still acceptable. We can see that the learning is almost okay. But then as you go to 100, doesn't work that well. I mean, sometimes it works a bit better than others. As usual, it's a stochastic algorithm, so every time you run it, you get different results, but still, it's not great. If you go to 1000 as scaling of the outputs, then it goes completely nuts. Can try to play with the learning rate. Okay, this helps a bit, but it's not able to learn as well as it was learning before. Like this time it's almost okay, but you can see that it has learned this weird behavior where it is actually piecewise linear instead of following the curvature of the real function. And we can try to make the scaling of the outputs now instead smaller. So 10 to the minus 1 is still okay-ish. But then 10 to the minus 2, it gets worse. 10 to the minus 3. Well, it handles better scaling towards smaller values and higher values for the outputs, at least. But still, its performance is not as good as it was before. So the best is if you try to maintain the scaling of inputs and outputs between -1 and 1. You can see here is where we get the best results. You can see the fitting now is basically perfect. The last parameters I've added here to play with is the batch size, but it doesn't play a super big role in performance, at least not in this example. Actually, I've noticed that higher values for the batch size tend to result sometimes in worse performance. It's a bit counterintuitive, but it's also pretty random. So like, for instance, now I just rerun it with the same batch size and the result is much better than it was. So there is not a very strong trend of performance getting better or worse as you play with the batch size. Also, I mean, we are not changing a lot the batch size. It's only between 5 and 20. In theory, what you could expect is that using a higher batch size, your stochastic gradient becomes more deterministic, because as the batch size tends to the size of the whole data set, then you go towards like classic gradient descent, and you're no longer stochastic, because every time you're seeing all the data set, and so the gradient is always consistent. It doesn't depend on the sampling, basically. So in this example, I think it's too small to see this kind of effect. But in case you saw that there was too much noise on the loss function during training, you could try to make the training process more deterministic by increasing the batch size. But for this example, we cannot really see that. Okay. So that's basically everything I wanted to show you. If you want, you can use the rest of the time we have together, which is roughly half an hour, for playing a bit with the script. And I remain here in case you have questions or doubts or things that you want to ask me. Next 2 lessons, because we have only 2 lessons left before the end of the course, it's going to be on Friday and we're going to talk about policy gradient methods, which is another family of reinforcement learning algorithms, which is quite different from everything we have seen so far. And with policy gradient method, we will finally be able to have policies with continuous actions, which is something new we haven't been able to do so far. And then the very last lecture, which is not going to be next Monday, because next Monday is bank holiday in Italy. It's the 8th of December. So don't come to class. I think university is going to be closed. So it's going to be Friday next week, the very last lecture. I'm going to use that lecture just to draw some conclusions. We're going to discuss a bit of pros and cons of optimal control versus reinforcement learning. We're going to summarize a bit all the topics we have touched upon during this semester. And I'm going to give you the final project instructions so that you can start working on the projects. And I'm also give you some information about the final exam, so what you can expect as the final exam, how to prepare for the oral exam, and then that's it. Okay, then you're free to either stay here and play a bit with the code or move on to your next class.